All right.
Good evening.
Good evening. Yes, welcome. So, apologies for the late start. There was I pressed the wrong button. Happens sometimes.
It's all good.
Hap- Happens to the best of us and everyone else. Hi, welcome to the Tech Audio Chat. The Tech Audio chat where we do tech audio stuff and we talk about tech audio stuff and we demonstrate tech audio stuff. Yeah, there you go.
I was trying to think of what to add there, but yeah,
That's it. That's it.
that's
Uh,
the thing.
that's the thing. I'm Dan Reynolds. I I work in tech audio. I work in game audio. And I've been doing game audio for 20 years this year. In fact, I just had my ninth anniversary of starting work with Epic Games, which is pretty crazy.
Wow, congrats! 20 years.
Yeah, 20 years in game audio. My first paid gig was in 2005, working on a website, games on web. Web games back then were big deal. Flash games. Flash games. Flash is not allowed anymore. Flash was banned from the internet by Google. So that dates me. If you've never heard of that, it's now used almost entirely in the animation industry. I'm joined once again by Eric Buchholz, who also does tech audio.
Sometimes.
Sometimes tech audio. Yeah. Uh, and you also work at Epic. How long have you been there now? It's
Almost 2 years.
almost 2 years. What month did you join?
October.
October.
So what is that?
Cool.
Another
It's
3
coming up.
months?
Yeah. Exciting.
Time flies.
It does, but also I feel like you've been there for a really long time. Yeah, cool. And we got folks in the chat already. Steve and Patrick from Germany, 3
Wow.
a.m.
Staying up late.
Yeah, that's building in UE and listening. Yeah, but hey, that's we've all been there. Yeah, RIP Flash. Yeah, it's used in animation now. In fact, Adobe rebranded it as Adobe Animate.
Yeah, I didn't know it was still being used. I played my fair share of Newgrounds and what other places had Flash games back in the day.
Weeble stuff was the meat and potatoes of my internet
Okay.
experience back in the day. And in fact, I think Weeble stuff now has a TikTok. I don't know how it's doing, but I sometimes encounter it in the algorithm, which is always nostalgic. And also like a really weird perspective on like my personality and how I've changed over the years. Because it's a very specific type of humor. Yeah, and in fact a lot of 2D animation, for people who don't know, animation, 2D animation and traditional animation are like hobbies of mine. And a lot of 2D animation, particularly domestic 2D animation. Well, there's not really much domestic 2D animation happening anymore. But a lot of 2D animation these days is utilizing Flash. Interestingly enough, one of the forefront programs for authoring Flash content for 2D animation is not Adobe Animate. It's Toon Boom Harmony. And so, yeah, that's
Toon Boom Harmony.
So Toon Boom is the company, and Harmony is the application, and it's not cheap. So, I mean, it's like a professional application for authoring.
Which software do you use for?
That's a good question. But I don't. There are two sort of there's a split in 2D animation, and that is the sort of flash side of things. And the flash side of things is where you have um, all all or almost all of your content is vector based, and so you can apply transformations to it
Right.
very easily and very cleanly. And so a lot of cartoon, especially cartoons in the U.S. are like talking heads sort of stuff, and so it's it's really easy to do that in Flash because you get to because you can basically reuse assets over and over and
Mhm.
over again. And the actual animation process is a lot more. It's some ways it's an interesting medium between 3D animation, which is essentially completely puppetry, and 2D animation, which is like traditional hand drawn animation, which is all hand drawn. So it sort of sits between those two spaces because it's a lot of puppetry happens in that
Mhm.
in Flash style animation. In fact, they have rigs, like you'll have complete rigs, and you know you'll have deformations and other stuff to sort of create the animation. And so I am not as much into that. I like drawing. It's like I like drawing. I like painting, that sort of stuff. And so my interest is in traditional animation. In fact, you kind of see this blurry. I blur this out because my room's a mess almost all the time. But this is actually a traditional animation easel. So this has a little light function. I don't know if it's on this side or the other side. Turns
Hmm.
on.
Nice.
Um, that stuff's really hard.
Yeah, I bet.
That's how I started out. Was just literally just not on this easel. I had like a cheap light pad from Huan. It was like
Hmm.
it's just like a little. It's like for tracing. I was like, I can use this, and I glued a pegboard to it and just started from there. And I'll tell you what, folks, animation is the most work I've ever done for something with the least amount of accolade. Like like I spend 3 weeks on something and then show it to someone and they go, "Huh, neat."
Has there been any in all of your explorations of animation? Has there been anything that's like kind of come back and helped you with
Oh,
audio, or just
absolutely.
like it
Yes.
helped inform either your creative process or just kind of decisions you make? Trying to bring it back into tech
Oh,
audio
yeah,
here, but
yeah, 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 it's not hard to have me derail the conversation. Yes, absolutely. So first of all, I would actually so I believe this in all sort of like one thing that I would recommend to people, especially if you're starting out, but just in general, explore other media. Like it's like explore creating other media, not just enjoying it. I think we can all enjoy lots of different, like a high variety of media. That's always good, but because and apply appreciation to it. But real appreciation comes from the creative process, the actual making things, and you can learn so much from anything else. Like it's a very, I think it's it's an exercise. It's not always going to be like a one-to-one mapping. It's like, how do I abstract this idea?
mm,
How do I bring this back? Sometimes it's more work than not. Sometimes it's very easy. In animation, I think there are a lot of things that apply to the sound design process and in music composition because it's a time-based medium.
mhm.
And so there are dimensions to animation principles that have a very easy mapping function back to music, back to sound design. And and the only reason I oftentimes don't like distinguishing those two things, but in this case, I'm very specifically talking about the sort of compositional process. In both cases, I'm sort of talking about the compositional process, right? So, um, for example, part of the history of animation in the US involves Disney, obviously. Um, and in the really early days of Disney, there's the sort of like canon of 9 animators that are celebrated for all time. They're referred reverently to as the 9 old men. And, 2 of them, Ollie Johnston and Frank Thomas, authored a book called The Illusion of Life. And it's it's a really interesting book. If you like animation at all, particularly Disney animation, if you have any interest in that, it's a really interesting book in general. But it goes it talks about both the history of Disney animation, and also these principles of animation that sort of worked out like a theory of animation, right? And there are a ton of what I would consider good practices that apply to animation that also could apply to sound design or music composition. And some, like for example, the canonical ones that they came up with. There's lots of different theories, but it's kind of like talking about the 8 elements of music or whatever. Sometimes they're like the 7 elements of music or whatever.
Mhm.
Um, it's kind of like that kind of principles. So that they outlined 12 of them, and I'm not gonna be able to knock them off the top of my head. But like for example, in animation, you have this principle of anticipation. And that is if you want to do some sort of gesture or movement or whatever, you want to animate something. It's it's good practice to apply an anticipatory movement. And we have this same idea
Yeah.
in sound design, right? Like if you or in music, like if having some sort of anticipatory element precede the important thing can help in many different ways of creating contrast, like compositional contrast. In animation, comes from theater actually. So in animation, the sort of thinking with anticipation is that you are alerting the viewer to movement that's about to happen, usually. And so this in theater, this is really important because if you're gonna have a character do something on the stage and someone's looking over here, you want them to
Yeah,
look over
yeah.
here before it happens, and so you give them some kind of anticipation, which gives them the time to like shift their view or whatever to look over. And so we can like that's an interesting idea, and we can apply that pretty. I think that's one of those ones that maps a little bit better. They have this concept of squash and stretch. So, squash and stretch can help express impact and motion and stuff like that. But an important principle is to retain the sort of conceptual volume of the element, like the physicality of it. So if a ball and it squashes, it's also going to sort of like stretch out,
Mhm.
right? And so the idea is that you're retaining the volume is sort of like maintaining the physics and the believability of it or whatever.
Yeah.
And that you can think of the same way in sound design, where if you're going to make a sound really fast, um, maybe you want to make it sound thin, as sort of a response to that change. And there's a certain sort of like adherence to the physical representation and the expectation that we have for how that sound, or however you want to sort of break down
Yeah,
what
yeah.
the dimensions are. And so I think it's something that can help feed because I feel like you're going like I feel like as designers, as artists, as creators, we are accumulating and building a constant toolbox of things that we can sort of just reach.
Mhm.
And I feel like professionals in particular, and if you viewer out there are maybe aspiring, still working toward a career, or beginning of a career, I feel like that's one of those things that is something that you see a lot of professionals, because there's a question that sort of is asked all the time where like how do you work through writer's block, or how do you work through these sort
Yeah.
of creative blocks, right? And honestly, it's like, well, I can just fall back on these methods and these processes that have I've used over and over again, that I know well. And you can and that, like, at that stage, then it's just like it almost doesn't matter what you start out with. It's just, as long as you get over the sort of like, not to keep adding metaphors to it, but as long as you start getting as long as you push past the sort of static friction, and the wheel starts moving, then you're going, and then you've pushed past the block, and it can be pretty easy, even if it's not something like that you would feel, oh, this is inspired or whatever.
Just
You
trust
know?
the process.
Yeah, exactly. And I think the more processes that you can sort of toolbox, the more you can sort of reach in and go, well, in this scenario, maybe I'll try this, and just it gives me a starting point. So, in fact, that's what when I taught music theory, that was one of the things that I was very adamant on, because I did not like the way universities taught music theory. I didn't like it at all. It felt like strict adherence to rules in a
Mhm.
space that I wanted to be creative in, and they were telling me not to do the things that all my favorite composers did. And so I feel like, so when I taught music theory, I was more like, here, music theory is an ongoing discourse. It's just a conversation that you're participating in, and here are things to think about, like diatonic modes is an example, right? It's like keys are a fiction, like they're just something we made up. It's not like you know what I mean. It's just
Yeah.
we just decided, hey, the part of our conversation, part of our music theory discourse is like, here's consonance, here's dissonance, and functionally these are the ways that you can use that to create tension or relieve tension in your composition, right? And so something like the diatonic modes is a great example of like, here's some toolbox, like, what does this sound like? And I always went through the exercise with the students where I would like, you know uh not I would mutate the melody to like fit the different modes,
Hmm.
so just be like, what did that feel like? What was the emotional,
Yeah.
what do you think, what would be useful for sort of kind of work anyway. So so I definitely, yeah, to bring it back around to the idea of the variety, feed your art, feed your craft with ideas from outside. This is a really great segue, actually. Because one of the things that I want to talk about today, or I promised people to talk about today, is this sort of distance field experiment that I've played around with. And I was going to share my ideas and some of my code and get into the guts of it. So that's kind of what I was thinking about today, or tonight, I guess, or this morning for
Germany.
Patrick. Hey, Aaron. Aaron. I forget, Sendon or Kendon. Yeah, let me know. What did, out of curiosity, because I remember we said something, or you said something like something to do with tools. What are you planning on, if
Yeah,
anything?
I don't have too much to show tonight, but I do kind of want to dive into some of the view model stuff and the widgets and tools and UMG stuff. Like previously, we had done some demonstration of like making uh, preset widget editor
Yeah,
knobs and sliders and stuff, but we can actually do a bit more with view models in terms of tooling. And so I just want to kind of
that'd be
prime
awesome.
or put some examples out there of other things you can do if you have the aptitude for building tools. So
Well, I think that's something that's always worth revisiting because, well, first of all, I feel like we went really fast last time we explored that, and it was like just out, so I don't think anyone had like a chance to take a look at it, and sort
For
of
sure.
marinate. And I think it'd be a good one, but that's always a good one. I think a
Hmm.
lot of the tech audio work I feel is centered around systems building and tooling. Like those two things really go
Yeah.
hand in hand. All right. Well, I've got my thing set up. If you're okay with me going
Yeah,
first,
you go first.
cool. So speaking of, oh wait, actually, I have to share my screen here. Hold on a second. I'm about 1,000 today. Yeah. So speaking of thinking about other media. Oh, here we go. Where am I? Where am I? Buttons to press. There we go. So um, speaking of other media, uh, one thing that I often look at is rendering for possible inspiration. In general, I would recommend people if you want like a career in tech. I think what's really important is to just be curious a lot, just
Hmm.
be interested. And that kind of thing, it's a hard thing to tell people to do because it's like a response to things. But I think that curiosity is like a really helpful characteristic.
You never know where you're going to find like a new
Yeah,
idea or just a new approach or just some sort of inspiration.
yeah. I think that it's easy to sort of spiral out. I do that often. Like you get the Wikipedia breadcrumbs, and you're like, "How did I end up at this page?" Um, but uh, but yeah, so something that I've always been interested in, sort of hearing about. I've always felt like there's some utility in audio with these with sign distance field and distance fields in general. And n- maybe there is, maybe not. I don't know. But so we'll just say what are they? Basically, they're just like sort of a grid representing space where uh, each grid point is a metric of some distance, of a distance from a thing. And so they have lots of applications in rendering. There's like everywhere I turn, there's like, so I'm using distance fields for collision, or I'm using distance fields to define an object shape, that sort of stuff.
I've run
Where
into them just using materials for like UI and stuff. You can create like vectorized, like not really vectorized, but like a very high definition curves and stuff on like
Yeah,
on a material and stuff. I don't know the terminology there, but SDFs.
yeah. So yeah, and so that's the idea, is that you have sort of a field, a spatial representation of distance. It's like encoded in the data itself. And so yeah, I've got links in the description to this page and the wiki what this one here, which is an article about computing it, and it talks about, like, here's a one-dimensional representation of distance, and then like a two-dimensional representation of distance, right? And so on and so forth. And so yeah, and then I also brought up the Wikipedia. Here's like it representing a shape. And here's like a really vivid graphic,
Hmm.
where you can see the red area is outside of the object boundaries, and the green area is inside the object boundaries. And so yeah, so I was like, hey, I feel like I don't actually remember if there was any specific inspiration, but I feel like I was like, I feel like this could be used to represent attenuation and spatialization. And I started sort of exploring that concept. So that's the sort of impetus here. And I apologize. I'm running I think that it's my graphics card. I'm running a 2080 Ti that used to mean something. And so whenever I have the viewport in focus, my like frame rate drops. I don't know why exactly, but I think that that's the reason. I've been trying to resolve it ever since I started streaming, but for some reason. So anyway, I apologize for the frame rate. But yeah, so one of the so so one of the sort of canonical challenges in spatialization is ex- ex- sort of expressed here with this oxbow river shape. This is a sort of natural formation that rivers take, um, and it just has to do with water velocity eroding the outside more than it erodes the inside, and so this shape gets exaggerated over and over time until they actually merge, and then it becomes straight again, and then you end up with these weird like you know ponds that have like an arc and stuff like that. Anyway, it's very cool. It's all about watershed and erosion. But in the sort of traditional methods for spatialization, what we will do is we'll put like an audio component or some sort of representation of the source position, and we'll like stick it to this spline because oftentimes a spline is being used to represent some curve like this. A spline, by the way, is just a curve in 3D space. That's all it is.
It's that white
And
line in the middle
it's
there.
that white line in the middle. Yeah, I could get closer, but it gets infinitely smaller because that's.
And you can drag the points if you wanted to change the course of the
Yeah,
river.
exactly. Spline is a vector, and then I can like move and reshape it. And so artists love it. And they have Bezier handles to like control the sharpness of the curve. So you can do stuff like that. And so yeah, so and I guess I can walk through the this system that I developed. I'll actually delete the one I have on here. Um, uh, now, uh, what I decided to do in Unreal is to make it a component. And there's a couple reasons. One, I made it a scene component. I can get into that a little bit more, but basically, what I wanted was for it to have its own um, location data, its own transform data. Um, and then I wanted it to be a component because I wanted to be able to attach to actors in a scene. And so that was the idea. And I was like, okay. And so you can add it. I called it the sign. I called it the sound attenuation distance field, which is sad F.
The sad F
The sad
component.
F component. And you can see this project is the sad F test. um, but uh, but yeah, so I have a couple of properties here. This is not used. Um, the transform is used, but I'm not going to get into that necessarily. But anyway, uh, I have a distance field source type, and so basically it uses sub object, and I've created variants for point sources, spline sources, and static mesh sources. This is the spline source, and then it populates some data here. One is the object I want to build off of. In this case, uh, it's the water spline. So this drop down is populated with components, spline components attached to the owner, and then I can select it. And then, so if there's multiple splines, I can pick which one, basically.
Fancy.
Yeah. Um, and then, uh, and then I have like some basic attenuation data, right? So I have the like, attenuation function curve. So like say I want logarithmic, and then I have the inner radius and then fall off distance, which are your like standard attenuation like functions. And so with the just pop that in. If I switch over to overhead view, I can use the middle mouse button. I don't know if maybe you know how to use this.
Yeah.
Yeah, okay. This is a really good one. If you don't know, this is a great like easy thing. In the gr- uh, grid view, whatever in the grid views,
Wireframe.
the wireframe. Thank you. The wireframe views, you can hold down the middle mouse button. I think there's also a short key, and then stretch the mouse and drag, and it'll actually be a measuring tape. So when you're working in attenuation, this is a really useful tool because you can be like, oh, let's say my sound source is over here. I can be like, oh, I want it to be audible from this point in the map, and then I can be like, oh, all right, that's 10,000 or something like that. So that's 100 meters basically. Anyway, so I can sort of see the like sort of average, can kind of get like build my own little idea of the width. So it's like 600 and some thicker parts, where the bend sort of clusters around, and then 400 and something, some 400 and change in some of the thinner areas. So I can just sort of approximate maybe something like 500 where I had it. That was actually the default. And then the fall off distance. So we'll do something like 4,000. Just do that. So there are still parts of the map that don't get the audio. And then I have the voxel size and the sample width scale, which I'll get into in a second. But the voxel size is basically the resolution at which my data will be encoded. So, so yeah, so in other words, let's, if we go back to the grids here we were looking at before, how big is each grid? Because it's going to be quantizing the data, and that is potentially problematic, right? Because that means that our resolution is going to have a sort of discrete um, spatial representation, and it technically will zipper if we do like a continuous sampling. So, but higher resolution data is going to incur more memory, right? So there's a balance to be struck there, and it's not necessarily going to be the same solution, or the same answer in every potential scenario. Hey, Clint, thanks for joining. Hey, Angelite. Yeah, so I'm gonna go with 200 um, in this case. Uh, so that's gonna be basically a 2 meter by 2 meter by 2 meter um, box. Imagine, and then this is the sort of This is what I was talking about to Eric before the stream started. Was I haven't personally explored creating async tasks. It's sort of a new thing. I've used like existing async tasks, but I haven't like custom built my own tasks. And there are a lot of thread implications in terms of the data and data custody and all that sort of stuff and how you update it. And there's many different methods, and so it's been an interesting exploration. So I haven't implemented that, which means that when I generate the field, it's going to do a bunch of processing, and it's just going to stick for a second. It's a good time to sort of catch up on chat while it's generating. So I'm click the generate field button, and it's generating the field now, and Angelite, it's 4:40 a.m. So y'all are the early birds here. Welcome anyway. I'm glad we could wake up or stay late with you. Um, anyway, so it's saved, oh yeah, and then there's of course the sound that plays, and so I have this sound, and this meta sound um, is 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 pretty custom around this scenario, customized around the scenario. So I have uh, three sources. Um, I have these sort of distant and medium river sounds. Sorry, that one's not distant. This one's distant, and then I have this sort of roaring river sound. Sorry, these I meant for close. So some air, basically some, you know, to me in my mind, in my sound design mind, it represents the sort of midfield when you're right up on the river, and then here's like the sort of the lapping waves when you're right on the waves, and then this I wanted as a very sharply attenuated distant sound. So this is like the sort of the river at a distance. And so I've got these uh, attenuation functions here. So there's no spatialization. This is like I have to custom roll my spatialization basically. And so I'm feeding in left and right balance. So I'm playing the sound non-spatialized technically, and I'm feeding in left and right balance control. And then I'm interpolating it. Smoothing out the data that comes in. Remember, I said that it would zipper the sort of more granular your data. Hey, Charles, welcome. Even if it's just a brief one, I'm curious. Yeah, I will check that out. Aaron said, "Hey, just slap on an F scope slow task and call it a day." Uh, I'm yeah, yeah, sure. Well, I'm interested in exploring that. Anyway, I add a little fade in just to make sure that my data is not jumpy on the start. That like it initializes properly. Uh, and then I'm using the stereo panner for the left and right values respectively. I just sort of like um, so in other words, I'm balancing the uh, the left. I don't know why. What did I do this for? Why did I do it this way? It's very interesting. Okay. I'm not 100% sure why I
It
did
was a
this.
4:30 a.m.
It was, yeah, it was like a exactly. But I do add these. This is my like insurance. So this is basically making sure that this only gets loud when you're really close. So this is basically another layer of distance based attenuation on the source material, and it's really sharp on the close stuff. I want this stuff to have a really sharp curve fall off, um, because all of this stuff is gonna be heard, and so it's just a way to, like, add some dimension to it, and, if I were to optimize this, I'd have, like, some distance threshold at which I'd actually start playing the sound, but then I have a more gentler one for this function here, and I can kind of give you, like, let's see if we have a point 2. These are normalized values, by the way. So they're expecting a 0 to 1 input. So there's like a point 0.2 distance, and then if we were to do something like a point 0.5, 5, sort of midpoint. And then when we get close, say 0.8, and 0.8. You start to hear some of the detail laps come in. Anyway, as was recently discussed in the Discord, don't forget to reset your input values after your audition. Okay, so right, so then let's add this to the thing. There we go. Cleverly called my meta sound. And then hit play and hope I did everything correctly. So, if you look in the upper left-hand corner, you can see a sort of, might be hard to see. You can see a sort of like a grid of like three by three grid,
Hmm.
dark blue, red, and green. And basically, I'm sampling a 3 by 3 by 3 space around the listener. So I'm sampling all of the voxels around the listener. And my sample, we lost the details panel, but my sample width is a scaling factor for the sampling width. So in other words, I sort of approximated this to like the stereo width,
Hmm.
But in this case, I'm actually widening my sample. And the left and right, I have a transformation function, which I'll get into, where I take all that data and then I find the most significant value after attenuation function based on the left or right channel. And then that gets fed in as the the scalar value for that channel, which basically approximates. Oh, I sort of liken it to, let's say, if you were doing field recording, a very classic field recording microphone setup is to have like two cardioids that are separated by like a meter or something like that, and you get this really wide sound.
Hmm.
But the only difference between that and this is that um, I'm not doing a time delay. Now, if I did a time delay, I think that would like enhance the experience to a certain degree. And that would not be too difficult, actually. It would be pretty easy to implement because we have like an ITD function in meta sounds. But that is, that would be a way to like sort of plus it up. But yeah, so let's go walking. So let's see. Actually, let me also add um uh just add like the sound so you can see the meta sound is playing. All right. Okay. So what you're going to get is this sense of spatialization based on the difference between the left sample result and the right sample result. So you see on the left side, or you can see left side, for example, let's say red left, that's the middle left. Um, this is actually just the middle slice. I'm actually taking up and down. So this system supports spherical representations of the audio. So in other words, if we had like Dolby Atmos set up, like it'd be we could get sound from the sample from above, etc. So
Nice.
it would work for that sort of scenario. And so you can see here I've got 0.25 on the left that I'm getting, and 0.45 on the right, just as an example of the difference between the two values that I'm sampling. And so that is fed in and interpolated so that when I move around, it's smoothed, basically, right? And so we get this nice spatial representation of our sound source. The sound source, the audio component, is itself not like, it doesn't matter where it is located, because the spatial data is just feeding effectively encoded in this distance
Right.
field, right?
Yeah.
Now, what I'm doing is I'm actually encoding the raw distance data. So so it'll be like how many U units from, in this voxel, how many U units from the spline, or the closest spline, and it gives me that. So anyway, so something to think about is that you could technically encode whatever data you wanted about that distance information, right? It's just whatever you're willing to take on in terms of the memory cost.
Hmm.
And so you could conceivably encode things that are like other metrics, maybe like filter data, or it could be like something like, one of the things that I've seen where distance fields are used is like in global global illumination for like subreflection. So it's like, oh, this like an optimization for ray tracing, basically. When you're like, oh, this is close, of significant closeness, that this ray actually needs to do stuff inside this voxel, or it's like, I could just pass by this voxel. Anyway, what's nice is because I get just a raw distance representation of the closest. I basically, when I sample, I just take the closest, like the highest value. And so what happens is, if you go between these two, you can kind of like, well, I'm right in there. So let's get something where I'm sort of in between these. So here, it's about 60 and 60. 61 is on the right side. If I move toward the right side, it just smoothly starts working. And if we were in surround, I could encode the rears, and all that. It'd be really easy to do that. And so this kind of situation, if your audio component is sticking to the closest spline point, this oxbow is a scenario where the audio component would jump to another point in the spline, and that would cause like a weird thrashing on like the spatial representation. I also get this approach also doesn't incur the sort of like dreaded 90-degree offset. Like, if you've got a source that's like literally 90 degrees from offset from your your listener forward vector, then you get like zero happening in the other channel. That's impossible because I'm always sampling the field in both areas. So I'm just getting a scaled representation in the other ear. So, yeah.
Cool.
Yeah. Where are we on time? Do I have time to dig into this?
Oh, yeah. Plenty of
Yeah?
time.
Are we good? Okay, good. There we go. Look, this is the most important part. Charles says it makes sense. Yeah, Angel Eye, like I said, you could encode anything in that and interpret the data however you want. So, like, that's the other thing is that I'm just interpreting raw distance data, and then I'm applying these distance attenuation functions. But you could put other information in there. I've thought about ideas around maybe like encoding, like taking like a larger chunk of space and then encoding, um, maybe angles, significant angles or something like that, where you could be like, oh, I'm going to, because real quick before I get into the details, there are some downsides to what I've done here. First of all, this data is baked into the asset, right? So it's distance data, so that's but it's doesn't have any sense of where the direction is, like doesn't know anything about the location of anything. It's just how far is that space, that chunk of space from the thing. And that is also stored in memory. And so that is going to occupy memory. Now, whereas like the spatial function now, if you do like the spline component approach, component on spline component approach, then that is very taking very little memory up, and it's but it's taking, it's doing everything in real time processing. It's a very efficient process. So this is not, but also there's maybe some optimizations that I haven't explored, so I just haven't been bothered with that.
It's blue sky right here.
It is, yeah, exactly. And I think that's, to me, that's, I think, a really important thing. I know we've talked about this before, but I think it's really a good practice to sort of allow yourself a kind of unrestrained exploration when you're in the like R&D phase or the pre-production phase or the pre-production phase. Where you're just like, I have ideas and I want to explore them. Those are the kind of opportunity you want to sort of like get a sense of the value of those ideas before you start going, okay, now how do we make this like realistic?
Mhm.
So I think that's a good, there's a balance to be struck, obviously, because everything takes time. But I think that there is a lot of value in the sort of prototype process and the sort of exploration process. And yeah, so that's sort of where I'm at with this. Is I'm like, got this idea. It's not for work. I can just be like, oh, I have this idea. I want to see what happens, what comes of it. Um, Yeah, Steven. Yeah, and so this, like the problem in my mind, the problem to solve, because Steven was saying, hey, it could be good for lakes and stuff like that too. Yeah, not just bodies of water, but like the problem that I'm trying to solve is this idea where you need to be able to represent a very large object, medium to large sized object. Obviously, large can mean a lot of things in like video games because it's it's virtual. But medium to large size, relatively large object of ambiguous shape. Like that's another thing, is that's part of it, is like you need to represent it in a way that's like a complex shape that is clearly trying to represent a sound emission that isn't well resolved with just a single point.
Yeah, it's a tough problem.
Yeah, exactly. And so I was thinking, this could even be interesting for biomes. Like if you've got biome data encoded in your map, you could have a very like low resolution representation of that biome location stuff. So that when you're in a biome, not like you could sample, distances from biomes, all that sort of stuff. Like I can imagine that could be a really interesting, complex, large scale representation of this sort of problem. Anyway, so that was the problem that I'm trying to solve, and I want to represent spatialization in a way that is also not point based. So in other words, if you have like, let's, like it's something that very clearly scales up. Like, so for example, if you're in a let's say you're in one of those crazy Atmos theaters, or what's the DTS version? I remember.
Yeah, no.
Oro 3D, I think. Anyway, if you're in one of those theaters where it's like you've got 100 speakers, like this sort of thing would still work, and you'd be able to represent the sound source as like a band across the 3D spherical representation. Like that kind of stuff, I think could be an interesting output of this kind of
Hmm.
system. Hey, Nicholas, welcome. Nicholas asks, how do you bring in all of that detail upon getting closer without causing phasing issues in the previously existing audio? Um, so that's a great question. Some of that is just sort of sound design stuff. When you're dealing with noise, sound sources with like a lot of noise, you're going to you're phasing it. You're just not going to get a lot of coherency between sound sources, so you're not going to experience a lot of phasing. That's just something in general. I was playing three earlier. We were playing three audio sources, and two of them were particularly noisy. And so the if you think of noise as just like random values, and phasing occurs when you have a lot of coherency, when you have the when the shape of the noise, the amplitude of the noise is almost the same, and it creates like this weird delay effect because there's like weird cancellation that happens, or just like weird destruction and construction that's happening, and that gives you like almost like a comb filter, right? So that you don't really get that when you have really noisy sound sources, because the noise itself is essentially random, and so the coherency is very low. It's a good question though, and that's something to think about with sound design. Just noise can be your friend. You just have to use it very judiciously. Um, yeah, right. So yeah, so
Let's dive in.
let's dive in. Let's dive into the code.
I'm curious about the voxels and if you have like any like level of detail sort of thing on it, or is it uniform?
I didn't. Yeah, that's a good question. Hold on. I'm gonna let me. I'm gonna take a risk and close Unreal, just so that my frame rate goes back up. Um, but yeah. So the question. Let me go to the object declarations here. So the question you had was, sorry, what was it again?
Like level of
Oh,
detail. Like
level of detail.
do you have like smaller
No.
voxel samples when you're closer, and then further away they get bigger, just as like
Right.
optimization? Or
Yeah, so I've thought a lot about this as an optimization problem. So there are data structures that are. So I would consider my data structure a. Technically, it's a sparse spatial hash, but the it's not that sparse because the data is like sampled on almost every chunk of grid space. So it's only
okay,
skipped if there's no data. Like if my distance is 0 at the moment, if its distance is 0, then I don't save that. And if I sample space and I don't get a result, then I assume it's 0. So in other words, technically it's sparse in relation to everything else in the map. In other words, I don't sample the whole map. I sample just the
sure.
relevant space around the object. But it's there aren't like if I like one of the things that I was thinking about as like a really good optimization would be would be like if we like go back to our sort of example here, like see that maybe these let me zoom in here. See like these two squares are both 5. Like if there's somehow a way to merge that data,
Yeah.
that would be a great example. The challenge um comes from this, like in my spline example, it's constantly adjusting. And so I don't think that those sorts of things happen a lot. And so but I have explored other ideas. I just haven't tried them out. And so like another approach might be an octree, a sparse octree. And that would be where the octree could potentially, so an octree would be is like subdividing space into 8 octants, or if you could imagine like a 2D version would be quad tree. So like you imagine you can split space in half, and then half one dimension, half
Yeah.
another dimension,
Yeah.
half another dimension. So that's 8 little cubes that you get with octants. So what you could do there is you could have an octant that maybe represented the cumulative of, or like maybe represented like the average, or I don't know, like
Mhm.
maybe, yeah. And so you could just be like, I just don't care. I don't need to load, like I don't need to know about. I don't know. There's some way that the data could be condensed in those scenarios. But yeah, I mean it's a good question, and I don't know exactly. I'm not sure what the best approaches are, or if there's an approach that I haven't thought of.
Yeah. No worries.
Yeah, but that's um, also what does level of detail mean, and what is the scope of your your field? Like if the field is really big, then maybe maybe you just don't care about high resolution, but also the sample itself is near your ears, right? Like that's so like in this case, like in other words, broadly speaking, yes, you could implement other structures to condense the data for distance, right? But we only care about what's near us. Like, what is the data that's near us? So, in other words, another way of optimizing it might be something more along the lines of like bisecting the spatial grid such that I'm only loading in, kind of like world partition, where I'm only loading in the data
Right.
that's around me, and that the other data is like serialized on an asset or something like that. So that I definitely think would make a lot of sense. And so, and there are some data structures that might be better than a spatial hash. Um, Octrees get a little bit weird because they the like initial bisection when you bisect the space, you have like these, you have octants that are near each other, but they're like pretty far away in like the hierarchy. So that's the only sort of tricky part with octrees. And
Yeah.
there are some solutions there, but like yeah, it's so anyways, that is one way to think about it. Like you could, like I could cache the data. Right now I'm caching the data in the instance of the component. I could cache it on an asset, and then the asset could like be referenced. But yeah. Yeah, exactly. The cluster loading, yeah. Cluster loading. That could be an optimization. Okay. Okay. So let's get to the field. So here's the so I made some static functions that are basically just cosine functions. And this is used in part of in my 3D transformation. And this because I just have not read this book yet. So I have this book. I've purchased this book. I have not read this book yet. So because I feel like ambisonics is like I might be in some ways might be recreating some ambisonics. Um But, so I'm basically making a spherical representation of sound. But, yeah, anyway, so these are functions for the transformation of a channel. So in other words, I have this 3 by 3 by 3 grid concept, which is the sort of sampled field around the listener. And the, um and then what I do is I have, like, these, transformation matrices that, apply, additional attenuation to the field data. So in other words, I sample the field. So I sample the field around the listener, based on the listener's angle and azimuthal, sort of all that sort of stuff. And then what I do is I apply a transformation matrix on one on the field for one channel, and then another for another channel. And that's basically how it works. And then um, I just pass that data in. I take the max actually of all the output, and then I pass that in. It's sort of like a cheat there. Um, but yeah, so this is just some convenience. So it's so I can see, like, 0 degrees to like 180 degrees, just cosine function. And originally I played around with a struct as an element, and I just initially put a float in there because I was thinking, oh, maybe I want to encode more information in there. But during debugging, I ended up just swapping it out for a float value. And so yeah. Actually, let me get this a little bigger here. Is that easy to read?
Yeah, I can read it.
Yeah. Okay. Good. And so yeah. Okay. So here's my maps, and I have basically attenuation matrix maps. I have a bunch of helper functions. I have my matrix, which is um, int vector 3. Oh, so here's the actual um, int vector 3 is just 3 vectors. So and then the I call it matrix. Right, forward, and up values. That's sort of how I think of it. So like the uh the lateral, the forward, and the
Mhm.
vertical, right? So um scaling function, we'll get to that in a second. Let's see, get max value, we'll get that. This is what I talked about. I get the max value of the resultant transformation. Anyway, so here's like my maps. So here's the mono map, which I didn't end up doing anything with it really. But it's basically the coordinates and the value, right?
Mhm.
So here's the like stereo left map. Let me get this into the sort of see. But this is the middle slice. This is the top slice. This is the bottom slice, and then it's forward, middle, back, forward, middle, back. And you can see here I have the coordinates. Um, 0 is left, 1 is center, and then 2 is right. Similarly, for the x is the right coordinate, the y is the forward coordinate, and the z is the up coordinate. And so 0 would be the reverse of that vector direction. 1 is the center point, and um, 2 is the positive direction. I could have just done negative 0 positive, but I was um, it's kind of a thing when you get into spatial hashing, you want all of your data to be positive. You want unsigned data,
Yeah.
and so that's just why I ended up encoding it this way, unsigned. So yeah, and then I just have the same thing, and it's just this is no, there's no, this is not like there could probably be better functions for this, but this is like me earballing the like attenuation on that. I was like that looks like a good amount because this is not. necessarily like this quadrant is not whatever this section is not necessarily 67.5 degrees.
Okay. Yeah, I was
You know
gonna
what I mean?
ask
Like,
about, yeah.
so, but it's just like it feels like a good attenuation amount. Like I had Decimus up, and I had like the cosine function just sort of like eyeballing these like degree values. Anyway, so there's some, hand waving going on here. But the crux of it is that I'm just doing a transformation. So I sample the whole field, which is a lot of data that I'm sampling, right? I've got 9 by 9 by 9. And then I apply this transformation, and then I take the most significant value of the result, and that becomes the value. And so what's nice is about this approach, as I mentioned before, is it supports verticality and it supports like I could just create more maps. Like I could just be like, oh, we have a quad output. Here's a set of quad maps, for each channel. Basically every channel that you want to support. And I imagine we could set this up to because I don't know the ambisonic sonic sampling function. We could set it up to sample these vectors on ambisonics and result like an ambisonic scalar function, basically a scalar for um, the channels, Anyway, so that right. So then here's my what was I doing here? Yeah, see, I swapped it out. Oh no, this sorry, I did use this T map. That's what this is. These are all um static functions. These are all static functions. These are still static maps, sorry. There we go. It's just static maps. And then yeah, this is the scalar, so it just takes in the map and then apply it just oh, this is actually just building includes the matrix. And then yeah, okay, and then it's oh, I see, yeah. So it's applying the scale. It's applying this map to the yes. What is this doing? Comment all your code.
It made sense at 4:30 in the morning.
Well, I'm just going through the vector, and then I'm applying I'm getting a value if a value exists. So I'm passing in a map. I look for the key. Okay, yeah, interesting. Okay, well, this is getting a value. Yeah, so this one. Oh, sorry. Okay, sorry. This is not a static function. So this is a function on the map itself, and so basically what this is it allows me to scale two maps. So it basically it's like a multiplication function, basically.
Okay.
And so it takes two maps and then it scales them together. And then this one gets the most significant value out of the map. So this one just sort of gets the max value from the map. That's it. Um, and so and so the idea here is that I have these static maps, like the left channel. So I sample the field and then I want the left channel value. And then so I scale the sampled field with the left channel, and then I get like left channel oriented version of the field. And then I take the most significant value from that field value, and then that gets passed into the. So that's basically it. So when you
Hmm.
saw the sort of grid in the upper left-hand corner, you can imagine that that is being transformed by a function that is orienting it to either the left or right channel, and then it's getting the most significant value out of that result. And so that's sort of the idea of this, like these maps having these like degree offsets. So like here, the right map, the this is basically 1. This returns 1. And this returns 0, and so there could be like a really high value over in in this spot, but it'll return 0 for the right channel
Mm.
because that's not important. But if it's offset from the direct value, then yeah, then there might be something really high there. If the super high, even though it's a little bit off, that might still influence that. Does that make sense?
Yeah.
Yeah. So that's the idea. This is the f- this there could be some more elegant way to encode this information. Um and that's why I was sort of thinking like ambisonics functions could be interesting if like because then you could potentially have a because the nice thing about ambisonics is I forget which one. My brain forgets which one. The ambisonics, there's a one of the ambisonics variants. There's actually, I think, like 7 or 8 variants. One of the ambisonics variants encodes data where the first channel is like pressure data, and then every subsequent channel is basically a vector data. And so it's a lot like midside, where you have like a mid channel, which is your pressured channel, and then side, which is the vector channel, the left and right vector channel. And then you just do a transformation to like encode out. And so uh I could imagine encoding these in ambisonics um as a way to maybe scale the encoding, the like the static encoding.
Yeah.
Possibly, yeah. So that's I don't know. There's something there. Something there. Okay. Right. So then here's my distance field element. So this is the actual distance field. And like I said before, I initially made this like element, and then I ended up this is the thing that I ended up just I was like, yeah, screw it. I'll just use a float.
It
Cause
works.
yeah, it works. It works. I mean, because I was like, I didn't want to complicate the thing. And then when I was debugging, I was like early on, I was running into holes in my like spatial hashing. And so that was yeah, that was an issue. So I use this could be an optimization, by the way. This is I the so the map. Let me zoom in here. So basically, the field, each element has 2 components: the key, which is the index, and the value, which is the thing that we've stuffed in there, the data we put in there. And so spatial hashing. I've described spatial hashing before on my in my talks and stuff like that. But spatial hashing is a way to encode spatial coordinates and collapse them into a single dimension, which is your hash. And so, if you can imagine, let's say you've got a chessboard, like it's eight squares by 8 squares, right? But you're using like Cartesian coordinate system. Like you've got like 5.35 and for like the x coordinate, and then 7.08 for
Yeah.
for the y coordinate.
Hmm.
Well, you could sort of approximate those, be like, oh, let's round those down to 5 and 7 respectively, right? So they're like, in this is like in the 5 up 7 over square, and
Yeah.
so or I guess we 5 over 7 up in the way that I described it. Anyway, so if you were to give each square an index value, then you could just be like, oh, that's in square 9 or whatever,
Yeah.
so you'd be like very
A lot easier to specify what you're talking
yeah,
about.
exactly. And so what's nice is the function to get to that point is really easy because you go 8. You take your coordinates and then you just um, basically quantize them to 8 in one dimension, and then 8 um and then add 8 times 8 to that. So you get this like basically a value where it's basically, if you imagine a decimal system, we have like base 10 system. This is the same idea. That is
Mm.
basically a numerical hash, right? And we just start over, like we start counting over, right? 1 0 1 2 3 4 5 all the way
Yeah.
to 9, and then we add a value, and so we can represent, 100 spaces in two numbers. Like that's pretty cool. That's an encoding of space data. And so when you sort of abstract the concept of a decimal system, then you can have each of your dimensions be um, any size. So and we'll take a look at that. So here's the field data, and this is where we get the voxel size. And then I have things like the field bounds and getting a value and retrieving all that sort of stuff. But here's the sort of crux is getting a hash. So we get the hash index, this function, and here's the hashing function. So I take in a vector value, and I specify that it's a local vector because one of the things that I realized, it was actually a mistake that I made with Soundscape that I want to review, um, is that uh, when I did spatial hashing in Soundscape, is I did it as a global vector, which meant that I had to support a super wide space. Um, and so world like large world coordinates like really messed it up. Like I was like, because like if for people at home, if you don't know, when Unreal moved from normal coordinates, which is 32-bit floats, to doubles, so going from 32-bit to 64-bit, um, large world coordinates, the operable like space a map could support went from like 22 kilometers wide to like 80 million kilometers wide. So like right? So it's like going from a like city to like a small solar system. Like that's like the difference between like a 32-bit coordinate system and a 64-bit coordinate system. So because like Earth is like 96 million miles, right? Or something like that, 90 something miles, million miles from the sun. So you can imagine like, Venus distance and smaller is like the like how big your Unreal map could be. And so encoding spatial data globally, that was a big mistake that I made with Soundscape. And if I
You
were to
got to think
redo it,
bigger.
yeah. Well, it's in some ways you have to think smaller
Yeah.
and just know that that's not like it's not relevant. You don't need to know what's happening on the other side of the solar system, right?
Maybe you do. Maybe.
Maybe you do. Well, that's where you want your LOD data, right? But that's a different way
Yes.
to, yeah. But yeah, so here we just basically we're quanti so sorry. We're getting the local vector. The local vector comes in as bipolar values, right? So negative. The local vector means it's centered around the actor, or in this case, the component itself. And so that's why I mentioned the scene component. By making it a scene component, it can sort of express all of its data locally. In other words, the data itself stored on that component can be expressed as a difference from the component's location and the location offset for all of the local data. So this is coming in bipolar. It's already been transformed to local coming into this. Why I make sure to say in local vector, because sometimes I'm in taking world data, world relevant vector data. And so then I take my min bounds, which I've already sort of measured. That was like my early measurement. And then I minus the inbounds. So in other words, the min bounds, if because I don't know what the min bounds are, if the min bounds are negative values, then any negative vector value minus a negative value will result in a positive value. So it basically offsets all of my coordinate space to 0 at the minimum. So it's always going to be positive. It's always going to be unsigned. And that makes the spatial hash function work. Because the spatial hash function, there'll be collisions if you have negative values. It'll do weird things. So yeah, so here I intake my width hash, basically, my width coordinate. And I'm just taking basically I've got the voxel size, and I'm taking the voxel size because it's a float value, and I know I'm going to be doing a division function, so I want to make sure that I don't mess things up. So I am just sort of capping it. Like if I know this value is in centimeters. So if someone wants to measure smaller than a centimeter, tough cookies. Like like that's where I draw the line. Alternatively, I could have done something like small number, kind of small number, but I didn't want to support like sub centimeter sampling widths. Like I didn't want to do that. So, that was a design decision that I made.
I think
uh,
it's fair.
yeah, so I'm just flooring it and converting a 32-bit float basically to an unsigned integer 64, and then I just keep everything unsigned integer 64. Unsigned integer 64 just means I have a really high um, max numerical value. And the thing is, you end up getting really high numbers with not that high widths because you're basically cubing all of your dimensions, or your dimensions, basically your sort of average dimension or whatever. It's effectively like that. So you take your x width, and that's just all I'm doing is I'm taking the offset the new offset vector, which is the input vector, at x value, and then I'm dividing it by the quantized voxel, right? So if it's like, let's say the coordinate's like 70 and my voxel's like 50, it's going to be like 1. It's going to return 1. 1 and change, and then it's going to floor down. Hey, Subterranean. Hey, Eric. Thank you, Eric. Look at this. There's a man. What's up? Yeah, and so then so I do the same thing with y, except what I do is I also multiply the result by the field's x width value, right? So the total width of in the x direction. And so what that does is all of the y values are going to get out of the way of the x values, right? So it's unclaimed space basically in the number train. And then the same thing for the z, except that I do x and y. So just like I said, decimal place. Let's see if 0 through 9, and then you take 0 through 9 for the second decimal times 10, right? That's your second decimal is going to be 0 through 9, but it's times 10. And then if your third decimal place is your z dimension, then it's 0 through 9 times 10 times 10, right? And so that's everything that's in that third slot. So that's the same idea. Is I'm basically creating like a custom like decimal space with like variant dimensions in terms of how big the numbers can get in any like slot. And then I add all those values together and it spits out a hash. And so this way of doing spatial hashing will not result in any collisions. But it takes really high integer value because you're multiplying or you're multiplying these all together basically by the end of it, you get these really high values. So the idea of using an unsigned integer 64 is like I just want a bunch of space to work with so I don't have to think about it. But an optimization here would be trying to figure out the smallest like number size that I could store this value in,
Yeah.
and then so that would be a way to like if I'm like, oh, this field size is this size, so then maybe all I need is um like an integer 16-bit integer or something like that, right? And so 16-bit integer or yeah, which I think is like 16-bit is 65,000 or something like that. So that would be like um a significant reduction in the memory uh, for because when you start thinking about something like this, you're storing data in like like it really scales up, right? This kind of stuff is like a death by a thousand cuts.
Mhm.
And so, and then also the distance information. Like what is my farther, since I'm already, removing the millimeters, millimeter measurements. Or even by the voxel size, like whatever my sampling size, 200, 2 meters, 1 meter, whatever. Um, then, I could be dealing with pretty small value widths and heights and all sort of stuff. And so that stuff could also be reduced in terms of how I'm storing that information. So, how you're storing individual pieces of information. Right now it's floats, but it could be like another in 64. And if I went from a uint64 and a float 32-bit float down to two 16-bit values, then I'm removing, like, that's a huge memory savings because basically it's going from 96 bits of information down to 32 bits of information, right? So that could be like a pretty significant savings. So anyway, that's something to think about. Uh, and then here's I unhash. I don't end up using it. I thought I might use it for debugging purposes, so I wrote it. But here's it untangles the values, and gives a vector. This would be good for debugging. And then this is just sort of like some helper functions, related to converting the world locations. Um, there's a get value. So this is actually sampling the field. So remember, the field is like a big map of these integer keys and float values. So this is just a little get the value at the spot. It sort of creates a hash. So it gets a location, and then I feed out a distance value. I check to make sure that the location is within the bounds. Otherwise, I return like a false, like I did not retrieve a value. And then I just convert the world location that I'm provided to a local location, and then I get the hash value. I get the index from the nice. So the other thing is that hash. The nice thing about spatial hash functions like this is they're actually really easy. They're like fast functions. So they're like something that like adds and multiplies are like the bread and butter of CPUs. So like that sort of stuff is really easy to do. If I wanted to optimize this hashing function, I would get rid of this division. I would like create like a this value like if like maybe like earlier up, I could like create that value, so like outside of this function, so that it could just be referenced as like a const, because it doesn't actually need to be inside this function. So that's like that's like a really easy optimization. And This could also be optimized out. I could take this out of the function. It could be done somewhere else, but it's still going to necessarily be. This is going to happen every time, so I don't see anything wrong with it. But basically, if I remove this, either so there's a couple different things. I could take this value and then I could also invert it, so then it becomes a multiply instead of a divide, and that's actually better because I could get that set up in advance. Anyway, those are just some optimizations to consider there. Um, yeah, okay. So then, yeah, I'm just grabbing bounds. The is within bounds. That bounds check could be done outside, but again, one of those things. Um, yeah. Okay. So then, yeah. So setting the field. This is just the helper functions for setting the field. Setting the field. Okay. Let's go down here. Back to the field. So the min bounds is all the cache data. I cache the world location so I can reference it later. This is a little bit easier that way. And then yeah, this was a little struct that I ended up reusing over and over again. Min. This is something that I used for um, to simplify my sampling process. So like when I generate the field, when I generate the field, I noticed that the functions for generating the fields were the same and the only difference was like how I evaluated the distance itself. So in other words, generating the field data didn't matter what my source shape was or the object type. It only mattered at one certain point. So I ended up um, re I refactoring that function to get the specific to basically be generic, and then use a specific function for retrieving the data off of a specific object at that one point. We can take a look at that in a second. But yeah, so here's the SADF object and all the stuff that we talked about. The distance algorithm, right? Defaults to linear, the attenuation curve. I support. I actually haven't tested it, so I don't know how well it works. But technically, I support custom curve type, inner radius, fall off distance. This is the generate field function. The get bounds and ranges. So this is done as an abstract edit inline new default to instance U class. So in Unreal, this means that it's going to be it's going to generate a new object instance, um, and what is this? Sorry. This is going to generate a new object instance when you select the subtype. Abstract means that you can't like this won't show up basically. And so this is just basically this is a template class. And all the virtual functions here are meant to be overridden by the subclasses. And you can see here I started exploring tasks. Yeah, didn't follow through on that one. Okay. So here's a point source subvariant. So this one is like if you just have a single point source, you just treat it as a point source, which is like a normal, but then with a local offset. I provided that so you can be like offset, by 100 units or whatever. So I have three functions that I overrided. This one was just like returns the bounds, and it's just 0 0, like because there's the point source has no min and max bounds. It's just like literally the center point. The min and max are the same. And then the inner radius and fall off distance are like the max value. So this or max distance. This was the object I mentioned before, where I was like I wanted to cache these together. The min, the max, and the max distance, and so these are used to help me define the space that needs to be sampled, right? So I need to generate the field, but I don't need to generate the field for the whole map. I only need to generate the field for the extents, and so that's what's described here. And then I have a function for getting the closest location to a point, which is really easy because it's just the in vector plus the local offset. So that's like super simple. So that's because it's always going to be the same point basically, because it's a point source. And then this is okay. I don't know. I don't remember what this. I don't remember what returns a given component is valid. I don't remember why I needed that, but we'll find out. Maybe I implemented it differently somewhere else.
I realized I've been muted for quite a while now.
Oh yeah, were you giving feedback?
I mean, it seemed like you were accepting it, so it worked out on my end,
funny.
but nobody else heard it.
Oh right, yeah, because I do some fancy stuff with the spline and static mesh components. So the spline component and the static mesh, I'm actually just providing a name, and I generate a drop down using uProperty fanciness, which is like the get options function. And so what happens is um, there's a function that's only used by the editor, basically, to get the child a valid a list of all of the child components that are of this type. And so um, this function returns all of the spline components that are on the actor, the owning actor.
Yeah,
So
this get options was added in 5.5, I think, and it's
it's amazing.
also it works in Blueprint too. So the same thing, you can create a function. I think it has to be const and return an array of strings. But if you do that, you should be able to
Yeah,
select that as your function for basically
I
a
didn't have to make
dynamic
a
enum.
const. Mine was
Okay,
not const, so it works at least
or
natively. It
pure
works
pure. I
great.
mean, Blueprint pure.
Oh, I see. Yeah, that makes sense. Yeah, that makes a lot of sense. I didn't need to designate that.
Okay.
Is that U function specifier? I forget.
It is, but I don't think you is Blueprint
Blueprint
pure.
pure. Okay.
But if it works, it works, right?
Yeah.
So I think in Blueprint though, you might need to check. I could be wrong, but
Yeah.
it seems like the type of function you would mark as pure anyway. But
Yeah, because you wouldn't want to. Yeah, you wouldn't want to have to execute it. Yeah. Okay. So that's the idea here. Is that this basically just looks at the parent object. We can actually look at it real quick because it's the same for the static. I did the same thing for the static mesh class, but I just create a new like a blank array of strings. I um I empty my I have a cached map. Um, and there's a reason for this, but I have if I go back real quick here, you can see down here I have a string to object map. So in other words, this um, this could probably be optimized a little bit, but basically the idea here is I'm caching. This should probably be like a shared pointer or something like that. Anyway, I'm caching the spline maps that I find, or splines that I find, and so that I can retrieve them by name. But uh, this could probably be improved by making this a some sort of soft reference or like a weak reference, so that so there aren't any issues with this pointer in like garbage collection. Anyway, that's a interesting edge case I just thought of. Yeah, so then we just go through. We get the outer actor, and then whoops, we grab all of its actor components, and then we walk through them, and we check for spline component types. And then if we find a valid spline component, we get their name and then we add it to our map. And so basically, I'm generating a map of spline component names and their um, objects. And so I populate the list of strings which you select, and then that string is then used to retrieve the spline reference when generating the um, the map, the function. So the field. Sorry, yeah, let's go back to here. We go to generate field. There we go. And I basically do it as a void function where I return on the output here. I have distance field struct. So the generate field function is provided essentially a struct input, and um, I just clear it out. I empty it, and then I make sure that uh, this is valid. And the reason I do that is because well, uh, I think I don't remember why I did that actually. Anyway, I cache all of my bounds and range. So I get my bounds and ranges, then I cache the min and max extrema and the max distance. All of this is because I was exploring the idea of like separating out, like chunking this out as like a task. In which case I'd have to copy data out and then wait for it to be retrieved because it would not be thread safe otherwise. And so anyway, I'm just setting the field bounds, which is just the bounds plus or minus the max distance, and then getting the width, and then the bounds with the field width, right? Yeah, field width is 3 dimensions. Something when I was trying to debug some issues, I ended up making this a single uniform width in all dimensions, but I think it's a better optimization not to have to do that, especially if you have like a really long a long source shape. Anyway, I copy this stuff over, and then I get my component, which is like whatever this the oh yeah, this is the component that you actually add. Because remember, this is just an instance object that's stored on the component, and then so I have a reference to that, and that's important because that gives me my world location. That's where I know. That's how I know where I'm supposed to be.
The object needs something in the world to grab that information from.
Yeah, because I end up
Mhm.
working in world space when I do
Yeah.
the field generation, and then I convert it all back to local space. And so uh, and then I store it as local space in the actual
Mhm.
field. But there's just more of the functions that I needed worked in world space, so I just default to that.
Yeah.
In the process of genericizing this function, and so then I walk through. I have my bounds, basically my width generated from the bounds, right? I had the uh, the the object bounds, which is and then I sort of the max distance off of those dimensions. And so that represents the like chunk of space that I have to sample and test basically to generate the field. And so I walk through this is the thing that takes forever. So this is like a walk through all the dimensions, X, Y, and Z, and I just go through and I infer a coordinate midpoint. So this voxel size zero 0.5 is basically the midpoint of that vector because like the vector is basically the starting because I offset everything by the positive. So you can imagine,
Right.
when you quantize a value you've got a float value to like an integer value, you're you always want to go in the same direction. So I'm always flooring it, which means zero 0.5 is 0 and 1.5 is 1 and all that sort of stuff. They all round down. And so what that means is all of the values start. And so I just sort of wanted like instead of doing everything sort of shifted off to one direction, I grab the midpoint. And so that's what this is. Voxel size. So I take the x, I multiply it by uh oh, actually this is x. You know what I did actually? This is an interesting story. So I was running into issues where I was getting holes in my field. And so this was actually me exploring oversampling.
Okay.
Sorry. So this is actually because it's x multiplied by half size voxel size, but I'm also going by 2. So this is basically I'm oversampling my field. This is one of the issues I ran into, I suspect was the issue I was running into, was I was getting edge cases where my hashing function was resulting in a non-grid space, like grid space that I didn't hash before. And so um and oversampling resolved it. Like that was
Hey, if it
Eh,
works.
yeah, like I was all like my hashing function was working correctly. It was just like that data was not available, you know? And so, um, So I'm not 100%. This is the thing, I'm not 100% sure why this was happening, but oversampling was the result, the fix. And I suspect it has something to do with my sampling function and the way that I am, um, like, getting the left and right values because I'm getting it based on I have to do, like, an angle transformation because the listener
Mhm.
is, like, orienting around space, and so I sample vector we'll get to that, but I sample off of the listener's orientation. And so I wasn't sure if it was, like, getting 3D spaces that I wasn't hashing correctly or something like that. Like, some sort of, like, like, where it's, like, the float value ends up there's, like, enough, like, noise in the float that, like, it's, like, offset, and then it's just, like, an
Yeah.
empty space for some reason because it ended up, but so this resolved it really well, but then someone in community I was going through this and talking about, and I think that I was rubber ducking the process with someone in the Discord, one of the Discord channels, and they had like they said something that was like, "Oh, wait, I screwed this up." Uh, this is why it's always good to talk to someone about the things you're
Yeah.
doing.
Share your work.
And I think I forget I have to look up what it is, but it was basically, I think so. Anyways, I did that fix. It was one of those dumb things, you know. I wasn't doing this thing. Now I'm gonna look it up. Anyway, going through blah 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 blah, blah and then get closest location to point. This is the thing that was always different. This is the only thing that was different was like how I get the distance. And oh yeah, this was I remember now. This is the thing that I was screwing up. So the set value function was what I was messing up, and that's because initially I was storing the attenuation scalar, and so it was more like an attenuation field.
Mm.
But that was really terrible because anytime I changed the attenuation function, I had to regenerate the
Oh,
field.
geez. Yeah.
And so it just made more sense to store the distance. And so I converted to distance. But in attenuation, how you pick the most significant value is inverted from distance. Because if I'm like dealing with a scalar, I want to take the most significant value. If I have a situation, so basically in the set value, what I do is I go and I get the value, I figure out what the value is, and then I look up that spot. Do I already have a value there? Right? I don't want to stomp a good value. If I've already because, like, for example, like, maybe it just worked out that I'm sampling the same location twice for some reason. The same box just ends up being in that same box. And then if I'm getting like, oh, this is the attenuation scalar from this point and the attenuation scalar from this point are different, I want to take the most significant attenuation scale because I want the loudest volume. But for distance, it's the opposite. I want to get the closest distance. So I had this. So I think that was what was going on.
Mm.
I have a suspicion that was going on. Either way, resolving both of those things, oversampling and this fixed. So yeah, that optimizing would be a scenario where we explore like, oh, how can we resolve this?
Yeah.
Anyway, yeah, and then and this was an important one. I mark the package dirty.
So you remember to regenerate?
Say that again.
What's it marking? This is
Oh,
the
so what happens
distance.
is this is basically the mark package dirty uh is a U object function
Yeah.
that will keep getting it will mark the owner chain dirty. And so what happens is this will mark the actor dirty, which will mark the map dirty. And
Yes.
so then saving it when I didn't have this, let's just say it didn't store the data between maps. So, because sometimes I would forget to save it or whatever, right? So this marks the map variant that way I save the data and say the data gets serialized properly in the instance. Anyway, so that's yeah. Anyway, so that's the generating fields. Yeah, and then the attenuation value. So instead of trying to like reuse, I just ported over the like raw attenuation functions. So this is the raw attenuation functions. Because I feel like I'm basically hand rolling my own attenuation function at this stage.
Mm,
And I didn't want all the baggage of like the current sound attenuation struct and all of its stuff, you know?
yeah.
I just wanted like the sort of the essentials. And so I just grabbed the function and just pulled that over. This could probably make this as a static function that then but I do use some cache data. Anyway, that's the gist of it. The only thing that we didn't look at is the actual component. So, well, here's the static mesh version. The static mesh version, so the static mesh version, I have to use. This is the only thing that I could find, and maybe there's something else. But get closest point on collision. So this one only works if simple collision has been applied to
Mm,
the component. So this is like something that I would have to explore. I would like to have to see if it already has simple. I don't know how to do that. I haven't messed with static meshes a lot, but I have to. Ideally, I would check to see if it already had collision. If it did, then I would just use that, and if it didn't, then I would have to apply it and
right.
then sample and then remove it. Right, and so like, so that's sort of like some massaging to happen. But I did test this, it does work. There's a question. Oh, hey, Subterranean. Angeli asks, weird question, hash world is quantized space or is it declared individual voxels? I don't know, what's the difference? So like when you look at something like a voxel game, voxelized game, game voxels, voxel graphics, I mean, included in that is like the voxel space that you walk through. Like it's I think the I'm not sure if there's a difference. If there is, I don't know. One thing I will say is that the spatial hashing is a method of indexing my voxels, right? There might be other ways to store that information. So that would be the distinction that I would draw here is that the method in which I'm storing the data could be different for different purposes. Yeah. Yeah, so that's a caveat, I would say, the collision thing. But then here's my actual component, and I just hide a bunch of categories because there's so much
Of course.
stuff on the scene component. Uh, and then do I do anything in the constructor? Oh, I just make sure that I can tick because I do use the tick. That's the only thing. I do use the tick. I've got begin, play, and play tick component. I cache an audio component on it, so it has an audio component. It has playing value as play and stop functions, so you can play it, you can stop it in the like in blueprints or whatever. Um, and although I ended up doing like that. I ended up managing that. Oh yeah, I guess we can do this. This is the guts of it. So here's the tick component. So this is the actual sampling during runtime, and you do all your standard like, oh, is the game engine, does it exist? Or global engine, I should say. Does it? Distance field source type, is that real? Is that a real thing? And then here are my vectors. And so then I go and get the audio device. And I get all of the listeners. There can be multiple listeners for each audio device. And then I walk through the listeners and I'm just, I did this could be optimized for like this could get messy on on split screen.
Yeah.
I usually like split screen is very much an afterthought for me. In split screen, there are multiple audio listeners, so uh, so they have different locations, and so that I could optimize it for that. But yeah, so then I get the listener transform, and then I get the location of the listener, the forward, right, and up vectors of the listener. So those would give me the spatial orientation of the listener. Then I make sure that the audio location is within bounds, because if it's out of bounds, then I don't care. I'm not going to render the sound. And then I do some micromanagement here for playing. And This one would probably fight with my API. So a fix up there would be to have like a state to like auto manage or not or something like that. And then it starts playing. If it's not playing, if it's inbounds and it's not playing, then it plays. Very simple. And then I start out with my sampled value. So there's two metrics going on here. There's actually there was the grid that you saw in the upper left hand corner, and then underneath that there was like another sample. That was part of my debug. With like the first thing I did was like, let's sample at the listener location and see if I'm getting good values. So that's sort of still remnants there. That isn't really this data that's not really used that much, but just for this debug here. And then I have my these vectors are for the debug message. But you can see here I have this is my field. So I sample the field, and if we look at the sample field function, this was like probably the most annoying function for me to write here. And that's because I get the world location vector. Here, let me go through it. World location vector, the forward, I pass in the forward vector, the right vector, the up vector, and then the sample width scale. Because then what I do is I have my sample width, so it's a voxel size by the sample width scale. So if it's 2.0, then and the voxel size is 200. That means I'm sampling 400 one way, 400 other way. And so you get really wide or really narrow, like you sort of control that. And then I go through my right, forward, and up vector values, right? Because I'm creating a field sampling, right? This matrix I talked about before at the very beginning, where it was like 0, 1, 2 for like negative direction, central positive
Hmm.
in that vector. And then I go right, forward, up. So I sort of crawl through this X, Y, and Z values effectively. I offset it because I am actually looking for negative. In this case, I'm looking for negative, not non positive directions. And so then I take basically, I get the sample location. In other words, I'm gonna sample this 9 by 9 by 9, or like 27 spaces. All right. And so I'm just going through 27 spaces around the listener. And the offset is the specific grid space that I'm sampling. And I just create a new sample location by taking the world location vector, and adding. So that's the center point. That's my listener. And then I am taking the right vector offset by the X value, the forward offset by the Y value, and the up offset by the Z value multiplied by the sample width. So in other words, I'm creating a vector in one of these like 27 quadrants, and then offsetting it by the width. So it ends up being like almost like a sphere around the player or listener. And then I get the value. So we looked at that function really early on, right? It just takes the sample location and distance value, and and then it returns. Remember it was like the most significant value, right? It was like, here we go, or what was it? No, this was yeah. This is giving me the distance value, and then I get, oh sorry, it's distance value at that spot, and then I get, yes, this just samples location, and then I run my attenuation function, and then I get my attenuation value as a output, and then I add that to my sample matrix. Remember, in the sample matrix is that 27, that was like one of these that we saw right up at the front here. This is what it looks like.
Yeah.
This is the sample matrix. And so this is giving me the field version of that. And then go back. Sorry, tick down here. Do. So this is the sample field that we get, and then I set up these stupid. This is my debug stuff. This stuff takes more time. This stuff would be optimized out pretty easily. Anyway, then if I have the audio component, is the audio component valid? I have, this is my transformation. So I scale by the left map and the scale by the right map. So I get the left map, right map. And then I get the max value from the left and right. And then I pass that in as a parameter into my meta sound. And then if we're playing and we're out of bounds, then stop playing. Yeah. So that manages the audio component, and it gives me the most significant spatial value in my sample field. That's it. That's the whole thing. Now everyone can do it at home.
Just a few lines of code.
Just a few lines of code. Yeah, cool. Any questions? Oh yeah, Angelite's got another question. So sorry. So the way I'm thinking about it, if we're quantized space as a linear gradient resampled from, let's say, 512 samples per 1 meter to like 4 samples per 1 meter per meter. So I think space is a linear gradient. I think I mean, it's effectively a gradient. I mean, it's the way the data that I'm storing could be visualized as a gradient, or thought of as a gradient. Is it? I mean, the difference is going from a continuous meter valuation, right, to a discrete evaluation. And in my case, it's like one sample per, like, 8 like cubic meters or something like that. So it's pretty chunky. Um,
And then interpolated.
I do a time interpolation.
Yes.
Yeah.
That's what I
So
meant,
it's,
sorry.
yeah. But to that point, I could sample more values and, in other words, create a like linear, like I sample the center value, so I could create like a function that interpolates it, but it's
Yeah.
maybe the offset, I don't know, and there could be a way to sort of know by simply knowing more about the like the field itself,
Hmm.
but it's still like, what does it mean to be like, so in other words, smoothing out all those functions requires more sampling, and more math, and that's usually just, that could scale up really fast because it becomes exponential when you talk about 3D space.
Yeah.
Uh, it just took longer than I thought it was going to take.
It'd be cool to make like a debug visual for it, I think.
Yes, I have played around with like draw debug functions for like that's part of my like testing my sampling, testing my field generation, because I was worried about that, you know, and though that's very expensive. Drawing all those boxes and stuff, and so I've done things like trying to find slices of it, but what would be really cool is is like a debug mode where it takes like where it draws maybe just the cubes around, like the grids around like your mouse point or something like that,
Mm.
Yeah, there it feels like there's some interesting ways to visualize that data, but it was gonna be a lot more work.
Yeah.
Yeah. So I bogarted a lot of the time. How do you feel about? Do you want to keep go? Do you want to keep going? Do you want to show your thing, or do you want to
Let's save it for next time.
save it for next time? Okay.
Yeah.
Cool. Yeah.
Um, yeah.
Yeah. Next time. Well, I don't know about next time, but one of the things that I have been exploring, which I posted recently, um, was updating my looper meta sounds
Mm.
and refactoring some of my looper utilities. And there's some things that I think could be fun to go over, but I don't know if it'll be ready next week. So, or if maybe I just show it like halfway state. So anyway, so yeah, we could save it for next week. Also, I think Aaron has talked about coming back or being sometimes on, or he says he's really interested in hanging out with us. He's like traveling today. He wasn't
Yeah.
here, but so Aaron might join us too.
Cool. Let's get the three of
That'd be fun.
us.
That'd be rad. Yeah, I've already set it up, so anticipated. Look at that, right?
There
Come
we go.
on.
Come back next week.
Yeah, come back next week. Who knows? Who knows gonna be here? Well, you should know beforehand because I'll set up a card. I'll find out next week who's gonna come on. Anyway, yeah, we sounds good. We'll do tech tools next week.
Works for me.
Cool. Well, let's see the system with convolution reverbs. Yeah, so I feel this is something that I feel very strongly about also. Convolution reverb is very much like global illumination. It's very similar kind of data. And so there is a possibility, like this is what I said, like this spatial hashing in general, what you store in that could be all kinds of information. And so if it's like acoustic measurements or some sort of vector information, who knows what that'd be, So anyway, I feel like there's a lot to explore in that space. And then calling back to sort of the original idea, like I think I think people should explore other media, explore other domains, because I think that you can be inspired by the things that other people are doing, even if they're trying to. Like sometimes they're solving very similar problems, and sometimes they're solving very different problems. But I feel like there's something to get out of that exploration. Always something to take away from it. So, yeah, be curious. Have hobbies. That's maybe a little confrontational. Like, be an interesting person.
Jeez. Okay.
All right. Thank you everyone for joining us. And have a good week. Stay cool and or warm, depending on where in the world you are.
See ya.
Thanks. See ya.